Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 23rd video lecture. And today we want to talk a little bit more about power series, in particular starting off with some examples having to do with the radius of convergence for a power series. You might remember that the radius of convergence is what we ended with during lecture 22, at least the definition of it. Then we're going to talk a little bit more about theorems related to series, and some of which apply to power series. We're also going to do the alternating series test for real numbers, and then we're going to probably end this lecture with absolute convergence of series. Okay, let's start off with some examples having to do with the radius of convergence. So here, my first example will be if we look at the series as n runs from 0 to infinity of n to the n, z to the n, and where we're thinking of 0 to the 0, we're going to look at it being equal to 1 in this particular case. So here, we're going to note, we want to talk about that series, that by looking at the limit suit, of the nth root of n to the n, we're looking at this part, to find that alpha from the previous theorem, we see that that's equal to the limit as n goes to infinity of the nth root and the nth power cancel with each other. This is n, I get infinity. And this is equal to, as I said, from that previous theorem that we had in lecture 22, towards the end, that's equal to our alpha. And so the r, which represents the radius of convergence, is equal to 1 over alpha, which is 1 over infinity, which equals to 0. And so what we're saying for this particular example, that is, this series, that guy converges on when z is equal to 0. Okay, we're going to look at another example. Our second example is to look at the power series as n runs from 0 to infinity of z to the n over n factorial. Now, in this, in terms of trying to figure out where it converges or diverges, this power series, we're going to use the ratio test. Here's what we get. We see that the lim suit of the norm or absolute value of z to the n plus 1 over n plus 1 factorial. You remember the ratio test is where you look at the a sub n plus 1 over the a sub n, so that would be z to the n over n plus 1, over n factorial inside absolute values. Well, that's going to be equal to the lim suit of the norm is z to the n plus 1 over n plus 1 factorial times the flip, which is n factorial over z to the n, which equals to the lim suit of the absolute value of the norm. Here, we just have a z in the top, and in the bottom, we're going to get an n plus 1. Okay? And that's equal to the norm of z, or the absolute value of z, as n runs from the lim suit here of, well, the absolute value of 1 over n plus 1 is just 1 over n plus 1. And we see that that part goes to 0. Okay? That's normal z times 0. which equals to 0. Okay, so that's less than 1. Okay, and so by the ratio test, I'll put that less than 1. So by the ratio test, this series converges for all z. Okay, that is the ratio, the radius of convergence, the radius of convergence. That's my R. I just want to finish it here. Is R equal to infinity? So that previous example, one we're still looking at, we're saying that that's how our series converges for all complex numbers, z. Okay. All right, let's do another example. So the series is n runs from 0 to infinity of z to the n. We want to look at it. So this is my example 3. Well, here we note that the lim sup of the c sub n's involved here, the nth root of them, well, the c sub n's are understood to be 1 in this situation. Okay, and so this is just going to be equal to 1. So by that previous theorem, thus the radius of the convergence is going to be equal to 1. So what we're saying here, if the norm of z is less than 1, then this series converges. And otherwise it does, not otherwise. And if the norm of z is bigger than 1, then this series diverges. Okay. And so the question becomes, what happens when the norm of z is equal to 1? Okay, well, let's look at that. So here's what I'm going to say. If the norm of z equals to 1, then what we can say in this particular series, this series, this power series, diverges. How can it diverge? It diverges by the divergence test. And here's the thinking. As the limit as n goes to infinity of z to the n is not 0. And the reason that this limit is not 0 is because, and this is with the norm of z, the absolute value of z being equal to 1. Because if it did converge, if the limit as n goes to infinity of z sub n did converge to 0, then there would exist a natural number of big N such that Okay? Such that for all n bigger than or equal to big N, what we have is that the norm of z sub n minus 0 will be less than any particular positive number that we pick. Now I'm going to pick 1/2. So that would mean that this norm or absolute value of z sub n will be less than 1/2 for all n bigger than or equal to this big natural number, big N that we have. But what we know is that the norm of z sub n in this situation is really equal to 1, which is greater than or equal to 1/2. And so that's a contradiction. So that's why this limited to 0. So by a divergence test, this series Zn diverges when the norm of z equals to 1. So that's an example, this particular type of series. The sum as n runs from 0 to infinity. This particular power series is an example where we don't know what happens exactly at the radius of convergence, okay? That it might diverge. That's an example where it does diverge at all points on the boundary for the radius of convergence. Okay, I'd like to look at another example, the last example. So fourthly, let's consider the sum of z to the n over n squared. All right. Well, note that the lim sup of the nth root of 1 over n squared. Well, instead of saying note that, we want to examine. So consider this lim sup. Well, here this is kind of tough to deal with. This ends up being 0 to the 0 indeterminate limit form. And so we're going to use a variation of this problem and get into L'Hopital's rule form. So we will note that the lim sup of ln of 1 over n squared raised to the 1 over n, which is ln of this function, if you will, equals, and so using properties of logarithm, we bring down to 1 over n. It's the lim sup of 1 over n times ln of 1 over n squared. And then here, this looks like, if you will, 0 times minus infinity, which I'll rewrite as lim sup of ln of 1 over n squared over n. And here I'm going to use L'Hopital's rule because this is like minus infinity over infinity. And here, the derivative here is going to be 1 over n squared times the derivative by the chain rule of 1 over n to the minus 2, which is going to be minus 2, 1 over n cubed, all divided by 1. Okay, so I forgot the lim sup here, so I made a big mistake. Don't forget the lim sup. Then there's the benefit of this quantity, which equals to the lim sup. And here it's simplified. It's going to have an n squared. It's going to be minus 2 over n. And that equals to 0. All right? Okay. And what we end up getting then is that the lim sup of the nth root of 1 over n squared is going to be equal to e to our answer here, which will be e to the 0, which equals to 1. Okay. So r is equal to 1 over 1, which equals to 1. Thus, what we're finding out is that this series, this power series, n running from 1 to infinity of z to the n over n squared, it converges if the norm of z is less than 1 and diverges, if the norm of z is bigger than 1. The question happens, what happens if the norm of z, or the absolute value of z, equals 1? Remember, z is a complex number here. Okay. Well, if z, then, if you look at the absolute value of z sub n over n squared, well, in the situation where the absolute value of z is 1, this is going to be equal to 1 over n squared. Okay? So, what can be said is that the absolute value of z sub n over n squared is less than or equal to 1 over n squared, because it's the same in this situation. And this series right here converges. Okay? So, by the comparison test, that's going to force this series z n over n squared converges when absolute value of z is equal to 1. So our last two examples show that we don't know what happens at that border. In that the third example, we had divergence at the border of the radius of convergence. And here we have convergence on the border, that is when r is equal to 1. Okay, next we're going to look at what I consider to be a little bit of a strange but useful theorem, and here's what it says. And we're going to use it later on in this lecture. It says, given two sequences, A sub n and B sub n, put A sub n equal to the sum as, if you will, k runs from 0 to n of A sub k. So here, I didn't denote this correctly. This should be n running from 0. And put A sub minus 1 equal to 0. So here, we can have A sub 0 would just be equal to A sub 0, okay? So that's allowed. So we're defining big A sub n for minus 1, for 0, 1, 2, and forever. Okay? Then, if 0 is less than or equal to p is less than or equal to q, we have that the sum of the a sub n times the b sub n, okay, and this is as n runs from p to q, will be equal to the sum as n runs from p to q minus 1 of a sub n times the quantity b sub n minus b sub n plus 1 plus, I'm running out of room here, so plus, that's the sum, this is not part of the sum, it's a sub q, b sub q, minus a sub p minus 1 times b sub p. That's what we want to prove. Very strange looking. But the proof's not so bad. It's notationally a little tough, but it's short at least. But here's our proof. Okay, so we're going to let big A sub n be equal to, these are partial sums. So as k runs from 0 to n of little a sub k, partial sums. Okay? If n is greater than or equal to 0. And we're going to define big A sub minus 1 to be equal to 0. Now, the first thing we're going to do is we're going to say, well, what if we're talking about some number, call it r, that's greater than or equal to 1? Let's talk about a sub r for a second. A sub r can be thought of as the sum as k runs from 0 to r of a sub k minus the sum as k runs from 0 to r minus 1 of a sub k. Because the only term that would be left would be a sub r when you subtract these term by term. But that's equal to, that's big A sub r minus big A sub r minus 1. Those are the partial sums. Now, if r equals to 0, okay, then a sub 0 is equal to the sum as k runs from 0 to 0 of a sub k, okay, minus 0, which equals to a sub 0 minus a sub minus 1. Okay? So, in conclusion, so for all r greater than or equal to 0, a sub r will be equal to big A sub r minus big A sub r minus 1. So that's some notation we have. Thus, if we look at what the statement involves, conclusion, the sum is n runs from p to q of a sub n, b sub n. We look at that series. Okay? That's going to be equal to the sum, rewriting this, is n runs from p to q, and the little a sub n, what I'm going to rewrite that as a sub, big A sub n minus big A sub n minus 1 times b sub n. Okay? Now let's work with it. So that sum now that we just wrote, that's going to be, you can break that up into two sums, if you will. So it's the sum as n runs from p to q of a sub n, b sub n, minus the sum as n runs from p to q of a sub n minus 1 times b sub n. Now, if we let, so here's the next line that I'm using. If we let j be equal to n minus 1, okay, letting that, we'd say this is equal to The sum is n runs from P to Q of A sub n, B to n, minus, here, we have the sum. Now, J is going to be n plus 1. So this will be, the J's would run from P plus 1. I'm sorry, P minus 1. So let me look at that. Yes, so the J is 1 less than P. That's what made me say there. So if P start, J is 1 less than N. So if N starts at P, then J is going to start at P minus 1, and it's going to go up to Q minus 1. Okay, so I'm letting J be equal to that in this sum only. Okay. And here I'm going to have, this will be A to the J, and here this is going to be B to the J plus 1. Yes. Okay. Now, that can be rewritten as being equal to, this is the sum as n runs from P to Q, A sub n, B sub n, minus this sum. I'm just going to rewrite this in terms of n's. So here I'm going to let n equal to j. So this is, it's not the same n again. I'm just translating them into the same index here. So I'm letting n be equal to j here. So it's P minus 1, to Q minus 1, A sub n, B to sub n plus 1. Okay. So that I have the same indexing here. So we're looking at this subtraction. Okay? All right. And so a lot of the terms overlap in terms of the index. So here's what we're going to get. That's going to be equal to, so I'm going to rewrite this as one sum. It's the sum, at least partially, as n runs from P to Q. Okay. No, Q minus 1. A sub n times B sub n minus B sub n plus 1. That's what we have. We'll factor out A sub n from those. But what we're going to have left over is the Qth term, which was going to be A sub Q, B sub Q. And then what we're going to have left over from the second sum is going to be when when n is equal to P minus 1. And that is A sub P minus 1 times B sub P. And that's what we were trying to get. Okay, so that ends that proof. Now, as a new theorem, suppose the partial sums A sub n of a series, little a sub n, form a bounded sequence okay? And when we start looking at a different sequence of real numbers, b sub 0 is less than or equal to b sub 1 is less than or equal to b sub 2, less than or equal to, so forth. This is a sequence of real numbers. And for this sequence, it also has the characteristic that the limit as n goes to infinity of the b sub n is equal to 0. This is a monotonically decreasing sequence, and its limit is 0. One of the things I want to tell you that indicates is that all of these terms in this sequence of real numbers have to be greater than or equal to 0. All right, then the conclusion is this series as of a sub n times b sub n converges. In that situation, that's what we'll have. Let's prove this. Okay. So, to prove, what we saw by observing is since that the a sub n is a bounded sequence, there exists an m that's going to be some positive number, such that the absolute value, remember this could be complex, of a sub n is going to be less than or equal to m. And that's true for all n that are natural numbers. So if we let epsilon be greater than 0, then since the b sub n's are greater than or equal to 0, and the limit as n goes to infinity of b sub n equals to 0, there exists integer, big N. We call it an integer. It's really a real, really a natural number. Okay. Such that for all n bigger than or equal to this big N, okay, the b sub n's will be less than epsilon over 2 times m. That's what we have. So this can be thought of as a new epsilon needed for the sequence, which we know converges. Okay. This is an equal sign, not a less than. Okay, don't get confused about that. And that's what we have. Okay, and this is true for all n bigger than that big N. Now, well, in particular, we could say, so b sub big N will be less than epsilon over 2 times n. Now, for p that's bigger than big N, but less than q, we have, and so here's where I start using the previous theorem. Okay, so the sum, the absolute value of the sum is n runs from p to q of a sub n, b sub n will be equal to absolute value of the sum as n runs from p to q minus 1 of a sub n times b sub n plus, it's plus, was it? No, it's minus b sub n plus 1, and then plus the a sub q, b sub q, minus, it was the a sub p minus 1, b sub p. And this is all in absolute values, which is less than or equal to, okay, so there's a everywhere, but really we'll break this up into, by the triangle quality, less than or equal to the absolute value of this guy, absolute value of this guy, and absolute value of this guy. And then we can bring the absolute value inside the sum. So we say the sum is n runs from p to q minus 1 of the absolute values of a sub n, b sub n minus b sub n plus 1, plus the absolute value of a sub q, b sub q, and plus, so I'll change this, the absolute value of a sub p minus 1, b sub p. And of course, you take the absolute value of each one of these items and the product will be the same. And so I will, that's equal to this sum. Show a little bit more details. This absolute value of a sub n, the absolute value of b sub n, minus b sub n plus 1, plus absolute value of a sub q, and that's the value of b sub q, plus the absolute value of a sub p minus 1 times absolute value of b sub p. Now, here, because of what we have chosen p and q by, and that the a sub n's are, well, just in general, not because of what we chose p and q by, the a sub n's being bounded, here I can replace each one of these with m. So this is going to be less than or equal to m times, so replace this with m and then bring it out, it's going to be bigger. And this is, I can replace each one of the absolute values of the big A's of whatever by m. So what we're going to get is the sum as n runs from p to q minus 1 of, here it's b sub n minus b sub n plus 1 inside absolute values, but those are real numbers. And then plus, so still m times this guy, and this is the absolute value of b sub q. Remember, this is positive number, so it'll just be b sub q. Okay. And remember we had them that they were decreasing, so this is really positive too. I'll just write them that way. B sub q plus b sub p. Okay, because all these quantities are positive here. And then, if you look at this sum here is less than or equal to, let's just equal to m. This sum, you have the b sub n's minus the b sub n plus 1s. They're going to have a lot of cancellations, and the only thing that's going to be left with is the b sub p. This is really describing the first term, and then the last term here is minus b sub q. And then plus b sub q plus b sub p. And so these two guys are going to cancel each other out, so we're going to be left with, this is m times 2b sub p. That's what we are. Just a little bit more for this purpose. But remember, the b's were a sequence that were decreasing, and so that's going to be less than or equal to m times b sub n, but and it's 2 of them here. I made a mistake, so put a 2 here. But the b sub n's were remember that was less than. It was 2m, and this was epsilon over 2m, which equals to epsilon. And so what that gives us, and here's what we're really using to prove this. So by the Cauchy criterion, for series, we get that this sum converges. And that's that proof. The next thing that I definitely want to get done is the alternating series test. So let's write it here. And it's for real numbers. Hence, for real numbers. And what it says is, suppose, okay, there's a couple things to suppose. First of all, there's three things. The first thing is that the norm of C1 is less than or equal to the norm of C2 is less than or equal to forever. Okay? B, that C sub 2m minus 1 is greater than or equal to 0, and C sub 2m is less than or equal to 0. And thirdly, that the limit as n goes to infinity of C sub n, so these are absolute values, remember we're talking about C being equals to 0, then what that says is that the series of the C sub n's converges. That converges. We won't prove that. So here's the proof. We let C sub 1 inside absolute values be greater than or equal to absolute value of C sub 2, be greater than or equal to absolute value of C sub 3, and so forth. Not only do we let that happen, we also let C sub 2m minus 1 be positive, be non-negative, and C sub 2m, so the even ones are non-positive. And we let the limit as n goes to infinity of C sub n be equal to 0. Okay. So here we consider a little trick. We let A sub n be equal to minus 1 to the n. And B sub n be equal to the absolute value of C sub n plus 1. Now, when you talk about the partial sums for the series of the little a sub n's, okay, here's what you're going to get. A sub 0 is going to be equal to 1. A sub 1 is going to be equal to 0. A sub 2 is going to be equal to 1. A sub 3 is going to be equal to 0, and so forth. And thus, what we find out is that this sequence of partial sums is bound. Okay? And these B sub n's, we have B sub 0 is going to be less than B sub 1, which is going to be less than or equal to B sub 2, less than forever. Now, since the limit as n goes to infinity of C sub n equals to 0, then that's going to force the limit as n goes to infinity of the absolute value of C sub n to be equal to 0. So that means that the B sub n's, the limit as n goes to infinity of the B sub n's, that's going to equal 0. I'll write that down here. Okay, so we're working on a way to use the previous theorem. So applying the previous theorem, Okay? Then the sum, as n runs from 0 to infinity, of -1 to the n, b to the n, will be equal to the sum as n runs from 1 to infinity of -1 to the n plus 1 times the absolute value of c sub n, okay, which equals, by the definition of the c sub n, the sum is n runs from 1 to infinity of c sub n, and that converges. That's what I wanted to show. Okay. I'd like to do one more theorem, and then maybe a definition. I think this theorem is good. So here we suppose the radius of convergence. This is a theorem, it's more like an example of convergence. Nicely. Of the power series of c sub n times z sub n is 1. And suppose that c sub 0 is less than or equal to c sub 1, which is less than or equal to c sub 2, and so forth. And the limit, we're also assuming this, as n goes to infinity of c sub n equals to 0. Then, this power series converges at every point in the circle, or on, I should say, on the circle, that's the value of z equals to 1, except possibly at z equals to 1. And so, just as a comment in this theorem, let us note that the c sub n's are real numbers. They have to be for us to be able to have the comparison that they are a decreasing sequence. Okay. Let us look at the proof of this. We let a sub n be equal to z raised to n. We let big A sub n be equal to the partial sums as k runs from 0 to n of z to the k. So the a sub n's and absolute value, remember this is complex numbers here. This is equal to the absolute value of the sum as k runs from 0 to n of z raised to the k. This is equal to the absolute value of 1 minus z to the n plus 1 over 1 minus z, which is equal to 1 minus z to the n plus 1 inside absolute values over 1 minus z. And that's going to be less than or equal to So that's going to be less than or equal to the absolute value of 1 plus the absolute value of z n plus 1 over 1 minus z inside absolute values, which is equal to 1 plus the absolute value of z to the n plus 1 over the absolute value of 1 minus z. And that's equal to, well, it's 2, because the absolute value of z, the z that we're talking about, is equal to 1. Is equal to 2 over 1, the absolute value of 1 minus z. That's what we have. So an is bounded by 2 over the absolute value of 1 minus z for all z whose absolute value is equal to 1, except with z being, except when z is equal to 1. Okay? And so what we're going to do is we're going to let b sub n be equal to c sub n. We're almost done. Then by previous theorem, then by a previous theorem, okay, this sum of the a sub n times b sub n as n runs from 0 to infinity, which equals to the sum as n runs from 0 to infinity of c sub n times d sub n converges for all z with the norm of z being equal to 1, except possibly possibly z equal to 1, and that's the proof. Okay, that's enough for today. I thank you very much for your time and patience.